Recently, I demonstrated the synthesis of potassium azide and potassium metal from readily available chemicals, but didn't film the decomposition of azide to the metal and didn't collect visible quantities of it. Today, I'm going to show this part by decomposing all the pure azide I have left, or around 6 grams. But even before we start, I want to emphasize that doing the decomposition at such a large scale is extremely dangerous, as you can no doubt tell from what is happening here. Thus, I strongly suggest decomposing no more than 1 gram of azide at a time. Also, I must reiterate that under no cases should an equivalent amount of sodium azide be used instead of potassium azide, as it is much less stable and will violently decompose and explode if heated only slightly. Anyways, with this lengthy safety instruction ahead, let's get back to the experiment. I placed the azide into a 250 ml flask and attached an adapter with a long hose to the open atmosphere. This long hose is designed to prevent air from reaching the flask after potassium metal has formed, but I can tell you beforehand that it wasn't necessary. I switched the feeble spall burners for a large one and carefully heated the azide to remove water and alcohol. I then strongly heated it at one point and the azide begins to melt quickly. To reduce explosion hazards, I didn't intend to melt all of the azide, but instead wanted to decompose part by part so that the reaction is more controlled. However, I found that it is impossible to heat some azide to decomposition temperature while keeping another portion of it solid. As the liquid potassium azide is further heated, it slowly starts to decompose and release some bubbles, probably nitrogen gas. The rate of gas evolution, as well as the appearance of the melt, is strikingly similar to that of sodium chloride in previous videos where I prepared perchlorate by a thermal decomposition method. When a large amount of gas is formed, it is important to further heat the liquid very carefully at the very edge of the liquid level. As my flame even slightly touched the liquid, the entire melt decomposed very rapidly and released enough nitrogen gas to blow the joint apart in a flash. But still, we did get some very nice footage of how this decomposition reaction progresses. Here is a slow-mo of the rapid decomposition you just saw. A yellow-brown color appeared at the place that contacts the flame, and the color quickly propagates through half of the melt. This yellow is potassium nitride, formed as an intermediate as potassium azide decomposes. Potassium nitride only exists for a very short time before rapidly releasing gas and forming an initially golden mirror of metallic potassium on the flask wall. You can also see that the flask is filled with a green vapor. Contrary to the belief of many people, this is the color of potassium in its vapor state. A few frames later, shiny white droplets of potassium metal slide down the interior of the flask, while the golden mirror turns to metallic with a tint of purple, characteristic of potassium oxide films. However, I'm still not sure what corresponds to the chromatic red, yellow, and turquoise substances, probably a mixture of potassium metal, potassium oxides, and potassium nitride. The bottom of the flask shows a shiny color which indicates that metallic potassium collects at the bottom. I let the flask cool for a bit, and after around 2 minutes, I added paraffin oil through the top of the adapter to protect the potassium from oxidation. After shaking the flask, you can clearly see some small shiny globules of potassium floating on the oil. I thought that this poor amount is everything produced by the reaction, so I added a few milliliters of absolute ethanol to wash the flask. A lot of gases are released from the adapter, but surprisingly there appeared to be a lot of potassium metal in the flask as a few large globules. I poured the contents of the flask into a beaker, and finally we can see some potassium metal made by the thermal decomposition of potassium azide. Based on the size of these globules, I think the amount we got here is around 2 or 3 grams. If that's actually the case, then the yield of the reaction is nearly quantitative, as I only used around 6 grams of azide initially. I shook the beaker to let the floating potassium contact with the ethanol at the bottom, and the oxide layers are rapidly removed, revealing 2 or 3 beautiful large globules of metallic potassium. Removing oxide layers on alkali metals by reacting with alcohol is a well-known trick commonly used in sodium purification, and as seen here, it also works with potassium. But since I didn't expect such large amounts of potassium to be produced, I added way too much ethanol, and the potassium reacted away quickly. After a few minutes, I was left with only one piece of potassium metal that solidified. I put it in a beaker of water to see the spectacular reaction, but the paraffin oil coated it and prevented contact with water. Considering that a piece of potassium metal as large as this is very dangerous if it actually started to react, I decided to directly dump it into the sink, and well, the results are basically what you'd expect. But anyways, I still have around 10 grams of potassium azide left over, and I'll look into producing potassium metal at a smaller scale. See you soon.